All right, greetings everyone. Welcome to the first part of the video for section 7.3. And we're going to continue on our process of learning about some new identities and how to use them to both solve equations and find some exact values of different ratios. So we're going to start by proving this identity here, which will then help lead us to a new identity. And so what we've got to prove is that the sine of 2a is equal to 2 times the sine of a times the cosine of a. And notice kind of what happens here from the left to the right is we start with twice the value of an angle on the inside of the sine, and we end up with just the angle itself over on the right hand side, which I think this may be the first time we've seen angles or identities like that. So here's what we're going to do to solve this is we're going to start with the left hand side, as we often do, which might not seem intuitive on this. We're going to rewrite that as, instead of sine of 2a, we're going to write it as sine of a plus a. And notice that's totally legal to do because a plus a is just 2a, right? Okay, so we have sine of a plus a, which hopefully now makes you think of an identity we had from the last section, which was that sine of alpha plus beta, right? It's one of our sum identities. And so in this case, a would be alpha, but a would also be beta. And so let's follow what that identity tells us. So it tells us that sine of alpha plus beta can be written as sine of alpha, which again is a, times cosine of beta, which again is a, plus cosine of alpha, which is a, times sine of alpha, which again is a. So this has now become sine of a times cosine of a plus cosine of a times sine of a. And then in our second term here, this cosine times sine, recall that you can do multiplication any order. Okay, 2 times 4 is the same as 4 times 2. So therefore I can rewrite that. Instead of cosine times sine, I can write it as sine times cosine. So what this will now become is sine of a times cosine of a plus sine of a times cosine of a. And now notice we're adding two of the same thing, right? We have a sine of a cosine of a plus a sine of a cosine of a. Add those two together. We'll just get 2 sine of a times cosine of a. Okay? And that's good because that's what we were trying to prove. Sweet. Wasn't that fun? Yeah, I agree that it was. Okay, so what that leads us to is a new set of identities called the double angle identities. So we see there at the top, the one we just proved. So sine of 2 times alpha or 2 times a gives us 2 times sine of a times cosine of a. And then we also have identities for cosine of 2a. And in this case, there's actually 3 options. So there's cosine squared minus sine squared, 1 minus 2 sine squared, and 2 times cosine squared minus 1. And as you might be wondering, for the cosine identities, when might we use each? And of course, the answer is it depends on the problem that we're working on, right? So the circumstances in the situation or the other stuff in the situation would probably, or other stuff in the problem, I should say, would probably dictate that. The other thing I'll say is you can hopefully see why these are called double angle identities, right? So inside of the trig functions on the left-hand side, we have an angle being multiplied by 2. And on the right-hand side, that's kind of been halved, right? The angles we're looking at are half of the original angles. Okay, and so that's an important distinction to make. And in fact, that will come up here. So notice we're given that sine of theta equals 3/5, and that, and that theta is in the second quadrant. And we're asked to find exact values for each of the following. And notice these are sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. Okay, so notice how what's in what we're looking for, the angle compares to the angle above, is it's double all of those, or all of those are double that, right? Which leads us to use one of our double angle identities. Now, we're going to find exact values for each of these things here. And as we do this, we're not going to find the actual measure of the angle theta. Now, I know we could using our calculators. We know how to do that using inverse sine in this case. But again, that's actually going to make this problem a little bit more messy than it needs to be, so we're not going to do that. So here's how we're going to start. So to find the sine of 2 theta, of course, we can use our identity, double angle identity, that tells us that that's equal to 2 times sine of theta times cosine of theta. Okay, and again, notice how the angle we're looking at has changed. It went from 2 theta to theta over here. And sine of theta, we know what that's equal to, right? From up above, we know that's equal to 3/5. So we can plug that value in. But then for the next part, we don't have what cosine of theta is equal to. So we need to figure that out. So how can we do that? Well, we go back to the information we're given about theta. We know it's sine, and we know that it's in the second quadrant. So what we'll do is we'll go ahead and draw a picture here off to the side. So again, theta is in the second quadrant. So we know that if we're going to draw out the angle, it would start here. Then it would rotate around into the second quadrant. And here's where theta would be. We also know, because its sine is 3/5, if you recall from chapter 6, chapter 5, I think it's chapter 5. We know that sine is equal to y over r. So we know that this is 3 over 5. So we have the value for y is 3, the value for r is 5. So we know the coordinates of the point right here at the end of the angle is going to be some x value, comma 3, because that's our y value. We also know that the distance from the origin out to that point is 5. And we know that cosine is given by x over r. So we need to find the value for x to find the cosine. Well, recall that one way we can do that is we can drop down a side here, make a right triangle. We'll know that this vertical side of the triangle is equal to 3, because that's the amount we go up to get to the point. And we need to find the value for x here, which we can do using the Pythagorean theorem. And I'll leave that up to you to double check, but in that case, we're going to get 4. But recall that we're in the second quadrant, right? And so because we're in the second quadrant, we know the values of x there are negative. So this should be a negative 4, which then tells us that the cosine value will be negative 4 over 5. All right, so then we can plug that in for the value of cosine here. So we have 2 times 3/5 times negative 4/5. Can make that 2, a 2 over 1. We multiply straight across. 2 times 3 times negative 4 should give us negative 24. Over 1 times 5 gives us 25. So the value of sine of 2 theta would be negative 24 over 25. All right, let's find cosine of 2 theta now. And if you recall from our previous slide, there are lots of options for what we can use for cosine. Cosine of 2 theta has 3 different sets of identities we can use. In this case, we could use any of them. But since we were given the sine of theta to begin with, I'm going to use the one that only uses sine of theta, and that was the 1 minus 2 times sine squared of theta, which again, we know the sine value, so this would be 1 minus 2 times 3/5 being squared, which we then can work this out. This would be 1 minus 2 times 3/5 squared would be 9/25. Do some fraction math here, make this a 2/1, make this a 1/1. Get some common denominators here, so we'd have 25/25 minus 18/25. Looks like we end up with 7/25 for the cosine of 2 theta. Okay, and again, notice in this process we have not found the value of theta, right? That was not important for us to find the sine and the cosine of 2 theta. All right, now I'm going to erase this out here. Yeah, sorry, I'm going to erase everything. Okay, to find the tangent now. Well, if you recall on that previous slide, there was no identity for tangent of 2 theta. But recall we have this handy dandy identity for tangent that always works. You know, the tangent can be written as sine over cosine. So tangent of 2 theta, we can write as sine of 2 theta over cosine of 2 theta. And we just calculated both of those values, right? We know the sine of 2 theta, we know the cosine of 2 theta, so we can plug those values in. So we will have negative 24/25 divided by 7/25. Do some fraction division there. So remember, we do our kind of keep change flip. So this would be negative 24/25 times 25/7. Cancel out the 25s. Multiply straight across. We'll end up with negative 24/7 as the exact value of the tangent of 2 theta there. Okay. All right. Thank you all for watching.